Yeah, thanks for the organizers for the invitation to give this talk. So I'll continue on some twistronic topic, in particular on twisted bilayer graphene. Well, I'm going to show some thermodynamic measurements of the strongly correlated gaps in the system, and basically just a little bit of a short intro, right? So I mean, probably throughout this workshop, we'll see really a lot of novel two-dimensional systems that can be basically performed with this Moray trick, where we induce a Moray superlattice to create flatbands in the system. And really, I just want to highlight that really by now, a lot of new sort of tricks and techniques have been developed to manipulate these flatbands in the systems. Again, twist angle Moray engineering, lattice mismatch Moray engineering, and also we can use these electrostatic gates to induce strong displacement fields to further tune the layers. And basically, I think the multitude of phases that we observe in the system so far, ranging for superconductivity, correlated effects, and also strong topological features, is really remarkable. So, but I will stick today to sort of the old thing, the twisted bilayer graphene with the magic angle. And I really want to just remind you that really the physics that governs the system is these flat bands, which appear at the magic angle condition of 1.1 degrees. These bands are ultra flat, right? They're in the orders of 10 MeV. If we include strain renormalization into the system, we also develop these band gaps that separate them from higher dispersive bands. And really, the flatness of the bands quenches the kinetic energy such that the interaction energy becomes dominant in the system. And the other ingredient, which of course also comes back all the time, is that really these mini brilliant zones that we create by twisting these 2 brilliant zones of the graphene lattice, these mini brilliant zones have different winding numbers, different barrier curvatures than the original graphene lattice, and really the bands are defined to be topological. So we have really this two ingredients, strong correlations and topology in the system. And really here, just a very short glimpse of sort of the different phases that we have been observing, often in one and the same devices, where really, if you look at the phase diagram of a typical transport measurement that we do in our group, where we measure Rxx as a function of filling, we observe really all these phases, such as correlated insulators at integer fillings. We observe superconductivity. We observe orbital magnetism. And then, in addition, we observe churn insulators in strange metals. And really, the topic of today's presentation will be mainly the question that really, from these phases that I have just highlighted to you, really there are two type of different type of electrons which are actually involved in all of these measurements, right? So basically, I talked about topology, superconductivity, strange metallicity, etc. Those are all involving itinerant electrons. So electrons that are not localized, that are like to propagate throughout the entire device, and which are highly mobile, right? And this is again given by these phases. And then on top of that, we also have these other phases which are responsible for some sort of localization type of physics, right? So in particular, of course, in STM, people see all these localized electrons in the AA lattice side. And really, these insulating states have to do with localized electrons that really are not mobile and are really sitting in the lattice sites. And so basically, this is going to be the topic of today, so to maybe get a little bit more intuition how these phases are paired. And I want to really highlight some previous work that has been sort of done to understand sort of the phase transitions across these insulating states. That has been done predominantly by Shahal Ilani and also by Ali Yazdani, where Shahal was using this inverse compressibility measurements across the phase transitions of the integer fillings. And he saw really this strong asymmetry in the capacitance when starting from an insulating state, you were hole doping or electron doping the system. So this strong asymmetry was really observed before. And the ongoing picture was that really there is some sort of interesting phase transition going on when we start filling the Moray to 1, 2, or 3 electrons per unit cell. And this Dirac revival picture, which has been developed, which really goes well with the symmetry breaking of the different flavors, spin or valley flavors that go along as we pass on through these transitions, and gives rise really to this asymmetric nature. So we were really highly inspired by this work, and so we wanted to do also on our own some thermodynamic measurements, and in particular Seebeck effect measurements. Okay, so this is the device architecture that we devised to study the Seebeck effect in the system. So basically, we constructed split-gated devices with transport that we can study transport on. So we have basically on the left-hand side of the device, we have a gate. On the right-hand side of the device, we have a gate. So we can really control the carrier concentration in the two different layers of the device independently. And we can also read out, of course, any type of photocurrent or photovoltage measurement between the different gated regions. At the same time, we can shine a laser light. This is all in an optoelectronic Attocube 800 cryostat. So basically, we can shine a laser light directly on the PN junction, and this light can induce a thermal gradient directly at the PN junctions, which then introduces a photovoltage or a photocurrent. And basically, by controlling the Seebeck coefficient separately in the two regions, we can basically drive the photovoltage that we can see here. And so basically, how do these devices work? So this is, first of all, of course, a characterization of the RxX map. So we are basically trying to use the two different split gates to track the position of the Fermi energy in the different devices. And our orientation point, of course, are the integer filling correlated insulators in the system. So this is basically a RxX measurement that you can see here as a function of the left gate and on the right gate. And really, every one of those lines here corresponds to the correlated insulator state to be traced by one of those gates. And therefore, we get this really, one gate controls this correlated insulator, the other gate controls this correlated insulator on the left-hand side, and so we get this characteristic checkerboard. And I really want to highlight, so again, this is the RxX line cut of such a device, and really, I want to highlight here that in our device, the filling factor 2 state has really the largest gap, which is much larger actually than the one, even what the resistance peak that we observe at charge neutrality. So we now take our measurement scheme on top of this double-gated map, and we basically now calibrate our laser such that we're really at extremely low powers in the linear regime of the excitation of the device. And this is what we see now in the photovoltage measurements, right? So we see basically strongly recurring features that are oscillating with the same type of periodicity as given by these correlated insulator states. And really what tells us about the mechanism that we are really developing here is in particular the behavior around the charge neutrality point of this double map that has been, of course, previously studied in detail in single-layer graphene devices. And this is what we see really in this, if we zoom into the charge neutrality point, we see this very characteristic 6-fold pattern of the photovoltage signal, where we, of course, get a sign change between the PN and NP regions, where really the Seebeck coefficient pulls the current into one direction. But we also see sign changes in these quadrants where, in principle, the Seebeck coefficient is of one type, but there's slight asymmetry between the values of the Seebeck coefficient, which also induces a sign change. And so this behavior is really indicative of the photothermoelectric effect as compared to other effects such as photovoltaic effect or volumetric effects that you can get in the system. And this is really directly analogous to what, for example, was done by Pablo 13 years ago now on single-layer graphene devices. So now what we can do, now having these maps, we can, of course, also look at the line cuts of this, in particular when we fix one Seebeck coefficient on one side to fix to 0, and we observe these photothermoelectric effect voltages as a function of filling factor. And what has really struck our eye here is that really at charge neutrality point, as you can see here, we observe really what is expected from an electron-hole symmetric situation. So at charge neutrality point, we observe on the hole side, we observe a positive Seebeck effect as expected from holes. On the electron side, we observe a negative photovoltage and a negative Seebeck coefficient as expected from electrons. And really the signal across this phase transition, across the transition over the gap here from electron to hole side is very highly symmetric. And this is, again, the same what people have seen in single layer graphene. However, if you look at the other gaps here at filling factor 1 and filling factor 2, and remember filling factor 2 was our largest gap, we really see an entirely different picture. So first of all, the signal is really asymmetric when we go across the transition. And furthermore, we don't see any sign changes, right? So somehow, even though here on the left-hand side we should have hole-like carriers, we do not. We only see a negative Seebeck coefficient corresponding to electrons. And so this is what I believe is very much consistent to what Shahal was measuring before in the Seebeck, in the inverse compressibility measurements. And so now we try to understand how this really can factor into our measurements. And so what we assumed is really two possible ingredients that can sort of explain this type of Seebeck measurements. First of all, we were assuming that there might be some mass asymmetry across the correlated insulator gap. So where really across this gap, one type of carriers has different mass than the other type of carriers in the electron excitations. However, such a mass asymmetry would only give us some asymmetric signal, but it wouldn't explain the sign it would still give us sign reversals. So the other ingredient, which is really important here then, is really to take account lifetime of the carriers. And if we now assume mass and lifetime asymmetry between the electron and hole excitations, really we can understand such a Seebeck coefficient that arises here. And really our theory colleagues in Andrei Bernovic and his group, they have calculated from such a two-band model, they have calculated such a Seebeck coefficient where really for just a fixed asymmetric mass, but just changing the lifetimes of the carriers would really result in this similar signal to ours, where really a strong asymmetry, but also shifting the dip to the hole side of the phase transition. Okay, so basically a natural explanation, and now I'm a little bit biased because, again, this is a theory developed by our colleagues, but a natural explanation is developing from the topological heavy fermion description, which again was introduced by Andrei Bernovic, where they were basically able to map the Bistritzer-McDonald model onto a heavy fermion model, and they basically were able to separate the electron degrees of freedom into basically two types of electrons. One, which is the heavy localized F-like electrons that likes to localize on the AA lattice sites, and in addition, you can find nearly free electrons that are also existent in the system, which are light and heavily mobile. Again, connecting those two physics of itinerant and localization physics. And so from this model, what they were able to do is calculate the energy gaps of the correlated insulator states, and they find really remarkable things. So first of all, for various states that they can use, so again, some different ground states can win in the system, they consistently find that the charge neutrality point, the excitations are always symmetric, they're electron-hole symmetric, just what we see in our measurements. But however, for all the other fillings, for the integer fillings of +1, +2, you always find this strong asymmetry between electron-hole excitations. So for example, if we take the filling factor 1 state here, if we electron excite the system, the first thing that we encounter is really these dispersive bands with light electrons that are highly itinerant and have a long lifetime. And if we do the hole excitations, we first hit these ultra-flat band regions with heavy fermions with a very short lifetime. And I want to say that, of course, because we were comparing our data with the theory, of course, what the theorists can do is they can completely turn off in their model the interactions. And this corresponds to basically a regime of ours where we can basically move to higher temperatures above the phase transition of the correlated insulators. And also there at high sort of non-interacting regime at high temperatures at 30 to 50 Kelvin, we can really fit our results really nicely with their non-interacting model. Okay, so with this, I want to wrap up. So I think I have a couple of minutes. Right, and I want to switch gears a little bit, and I want to talk about actually applications from twisted bilayer graphene. So I want to talk about single photon detectors that we can build out of the system. And basically, single photon detectors such as SNSPDs, superconducting nanovirus single photon detectors, are usually made from nano-patterned, ultra-thin, superconducting thin films, where really companies like Single Quantum, they pattern these meander-shaped lines into their superconductors. However, one limitation for these superconducting detectors is always the wavelength at which they can operate. Usually they operate at visible and near IR wavelengths, but at longer wavelengths they stop to work. And one of the reasons they stop to work is that the heat capacity of the superconducting thin film is not low enough in order to really get a click out of these low energy single photons. And so here, graphene has a remarkable property. So this was already discussed in Pablo's first paper on twisted bilayer graphene, is really that the carrier concentration of a magic angle graphene that gives rise to the superconducting state is extremely low. And it's record low in the sense that it's really orders of magnitude lower than the one of your traditional superconductor like aluminum, niobium, and many more. Okay, so basically now we wanted to see whether we can use this low heat capacity, low carrier concentration twisted bilayer graphene and the superconducting state thereof as a single photon detector. And this is basically the work that we did again with our superconducting devices. So we took a twisted bilayer graphene device with 4-thermal geometry. We were basically injecting laser light on it, very diluted in a very sort of attenuated fashion. And we were basically using the superconducting state of our device, where we tuned the bias voltage very close to the transition to the non-superconducting state. We use electrothermal feedback such that really whenever we heat the system enough to get rid of the superconductivity, really electrothermal feedback allows us for efficient cooling of the system, and so allows us to observe some clicking behavior. And so here is a video that you can see when we basically record the clicks in such a device as a function of bias voltage. So we started at bias voltage, which was far away from the superconducting transition, and we gradually shifted to the superconducting transition. So you see a lot of clicks that happen in the system until they're completely saturated. And really from the counting and the shot noise properties of these clicks, we can bind them now together and can show that really all these clicks show Poissonian statistics, that they're really independent of one another. And another thing, of course, which we can do here is to compare the count rate of the clicks to the to the power of the laser light that we're injecting on the system. So basically compare the count rate of the photons to the number of injected photons into the system. And this is shown here, where we really observe a linear behavior of the clicks as compared to the photon count as a number of photons coming in. And that really demonstrates that really these clicks come from single photon events and not from multiple photon events. And so with this, I really want to wrap up my talk. So I really want to thank the group, who is now really well settled now here in Munich. And I'm happy to answer all of your questions. Thanks.
Okay, we'll have time for one question, please. If nobody, I'm going to take the opportunity. Okay, there's one. Good.
Nobody's asking a question, so I must ask you a question.
Okay, hi.
So this, this interpretation in terms of all the heavy fermion and all that stuff, is that really essential to have that interpretation, or it's just a question of what the spectrum of states are?
Exactly, that's a good question. So basically, the first sort of our experimentalist interpretation is to try to understand the ingredients that can drive such a response, right? Without any theory involved. So our interpretation is really that there must be some mass and lifetime asymmetry across the phase transition, right? And now your question, I guess, is whether we need to stick to the heavy fermion model to explain it. And the answer is no. So in principle, any Hartree-Fock mean field theory would also give you a similar bands dispersions, right? But I think So in this case, it's universal to the theory we use. But I think what the heavy fermion model really does well, it really separates well the masses of the different electrons, right? It does a base transformation where it sort of thinks of electrons, of two types of electrons, one being heavy and one being light. And I think this is something which resonates well with the main ingredients here of mass and lifetime of symmetry. But any Hartree-Fock model would give you similar spectra, right?